Yeah, welcome everybody also from my side. So just to set the stage in this audience from the very beginning, I am a condensed matter experimental physicist. That's very important, okay? And that's my background. We grow materials in my lab, and we do thermal and electrical transport experiments in magnetic fields and low temperatures. So that is also the type of talk that you can expect now. Huh? And but in the end, I will phrase a few more questions that go beyond the experimental physics, and I hope that we can use this as a base for discussions afterwards. Okay, so from our point of view, right, if you look at conventional condensed matter systems, then of course when we measure transport, so electrical charge current or heat current, then what we measure is the current of quasi-particles. Yeah? And in normal metals, in very standard metals, you usually have parabolic band structures that look like this. On the right side here, that represent massive, or maybe in the high energy language, massive fermions, right? That are described by classical Schrödinger equations. However, there's a relatively new class of materials where such trivial materials or metals are converted into materials that obey a band inversion. For example, the easiest way to get this is spin-orbit coupling. And now the interesting thing of these materials, and my talk will be based on this kind of quasi-particle description, right, is that the low energy description of quasi-particles in such metals around these crossing points of these two bands, when you have spin-orbit coupling and a band inversion, is actually, a description of massless fermions, right? And the whole talk is based on this description of this low energy description of quasi-particles, electronic quasi-particles in metals, right? We call those metals either Weyl or Dirac metals, depending on whether these crossing points here fulfill Dirac or Weyl equations. The nice thing is about Weyl, so-called Weyl metals, is that you at hand in a single metal you get actually chiral particles that sit at different points in momentum space, right? So if you consider this this dispersion relation here, you could think of the green points here as left movers, and the yellow point here is right movers, and they represent chiral particles of +1 and -1. Okay. And just to make this, to overemphasize this a bit, so the idea basically in this field where we work on is that you now can transfer, right, the field theories that were originally developed in quantum field theory of the vacuum to our quasi-particles in condensed matter materials, but with rescaled parameters like the Fermi velocity instead of the velocity of light, and so on and so forth, right? And to really, to again set the stage, what we're really dealing with is metals. So I took a photo here just yesterday. I was quickly in the lab. This is, for example, a Weyl semi-metal or Weyl metal that we grow. It's called niobium phosphide, and as you can say, if you would be now live, I would really give you this at hand. So this is really a metal. Huh? It's a piece of metal that you can put in your cryostat. It has, first of all, nothing to do with black holes or gravity, except of that it has a weight on its own by itself. But it hosts these very special type of quasi-particles that act like massive Dirac or Weyl fermions. And a proof of this is usually given in our field by an ARPIS measurement. It's an angle resolved photo emission spectroscopy experiment where people probe the dispersion relation of electrons. And here on the left side, you can actually see a real ARPIS picture of the niobium crystals, and niobium phosphide crystals that I just show you. And you can really nicely see here on the left side the two Dirac, the two Weyl cones of different chirality at the Fermi level. Okay. So now that we have this beautiful chiral quasi-particles in our system, the first that people in our field thought of were quantum anomalies, to test quantum anomalies in a condensed matter system. And what I would like to start with, although it has nothing to do with gravity yet, is the so-called chiral anomaly, which was first discovered in the neutral pion decay in a collider experiment, right? How would this look like in a condensed matter experiment? So the mindset is this, the idea, right? If you consider a normal metal and you would apply a voltage to it, yeah, then you would expect that you get a current flow, right? Because you have states at the Fermi energy and you simply have a current flow. Now, if you consider a Y semimetal, like on the right side here, and your Fermi level is just above the Y cones, you also have a finite density of states at the Fermi energy. So if you apply a current, you would expect a voltage to measure, right? Or if other way around, if you apply a voltage, then you would expect a current flow. However, it turns out that current flow in these metals is surprisingly suppressed. So you apply a voltage, you expect, if you just consider the DOS, density of states, a certain current, but it's heavily suppressed, right? And the answer, so why it is suppressed is that these two cones here, right, are effective or governed by the law of the chiral symmetry. So if you would consider, for example, here, this is a very, very zeroth order model, right? But if you would consider a band structure like this on the left, on the right side here, these green left movers here, or the particles here on the left cone, these are left movers, and here on the right side, these are right movers, right? But on the same time, right movers are particles with one chirality, and left movers are particles or quasi-particles with the other chirality. No? So in thermal equilibrium, when you have no voltage applied, you have in the zero order model the same amount of chiral particles, the same amount of +1 and -1 chiral particles, and you have no current flow, right? Because you have this, if in thermal equilibrium, you have the same amount of left and right movers. Now, if you would apply a current, then some of the left movers would be converted to right movers, usually, right? Because otherwise you wouldn't get a net current. However, in a Y semimetal, this would mean that you convert particles or electrons with one chirality to the other side, and this is forbidden by symmetry, right? And this, in effect, you would usually think it would not be observable, but it is indeed observable. No? And now the idea is, like for the chiral anomaly in the collider experiments, if you apply now a magnetic field in parallel to your electric field, then suddenly the breaking of the chiral symmetry is allowed, and you should see a current flow. So this is this conceptual framework. And you can actually also do calculations on this. These graphs here that you can see here, this is a calculation by a colleague of mine, Tobias Meng, and it's based on a theory that has been developed by one of our, I hope he's in the audience, Karl Landsteiner, actually. It's just a numeric calculation of the chiral anomaly for such a Y semimetal. And this is what you would expect as a function of magnetic field in such a configuration, as you can see here on the left side. Sorry, this is the prediction for an electrical conductance measurement, okay, on such a metal. And indeed, we have tried this on Y semimetals, so did this experiment and see if we could see signatures of this chiral anomaly in our materials. We were not the first. There were other groups that did this before us. But the general features are all the same, always the same. So imagine you have here a metal, right? And for this experiment, you forget basically all this complicated contact lines here. It's just a metal placed on an insulator, okay? And what we do now is we apply a voltage between these 2 points of our little metal and measure the current flow in this circuit here, okay? That's all. And we do that as a function of magnetic field, and first applied perpendicular to the current flow through this wire, and then, or to the voltage applied to this wire, and then a second experiment as a function of the a magnetic field that is applied in parallel to this experiment. And if you do that, you can see our first experiment when the magnetic field is applied perpendicular here, and you can see that the electrical conductance is heavily suppressed in magnetic field and very low, right? However, if you now rotate the magnetic field in the plane of the current, in the direction of the current, until it's parallel, you can actually see that the current flow is strongly enhanced, and the shape of this magnetoconductance here is consistent with the predicted shape for a chiral anomaly in these systems. Okay, so far so good. This was actually nothing new when we started this. It just was also for us a good cross-check whether the stage is set for further experiment. And like others, we also thought, okay, now that we have such a nice system where this anomalous physics obviously comes into play, can we go actually a bit beyond the experiments and do maybe even an experiment that has not been done in high energy physics before? And one problem that we came across is the so-called axial gravitational anomaly. So this is also a quantum anomaly like the chiral anomaly, but now it's said that the chiral symmetry is broken under strong gravitational fields instead of electromagnetic fields. However, this is extremely hard to be tested because the strength of the gravitational fields that you would need for such experiments and to observe the chiral anomaly or the so-called axial gravitational anomaly in real gravitational fields, they actually do not exist on Earth or in any experiments. According to Karl Landsteiner, you would need gravitational fields as big as close to a black hole, and we cannot do experiments in this framework, right? But when I think I was a PhD student even then, I came across a fantastic paper from Lattinger. You probably all know this one. It's called Theory of Thermal Transport Coefficients, where he tries to implement temperature gradients into field theory to actually calculate thermal transport, because that's apparently very difficult. And he found out that in some sense, under some in the relativistic limit, temperature gradients act like gravitational fields. And I was kind of naive during that time and said, wow, that's fantastic. So let's go in and try, because we can apply temperature gradients to our materials and measure heat transport or thermoelectric transport. Let's try if we see in a similar manner as the chiral anomaly, also the gravitational anomaly. However, this is until now highly questionable if the Lattinger picture and approach actually includes anomalous responses. And I have been told very early by my theory collaborators that this path is highly unknown, right? At the same time, when I read this paper, there was a second paper by Subir Sachdev's group, and they were actually predicting that the gravitational anomaly is observable in Y semimetals in thermal transport experiments. However, only they made predictions based on a hydrodynamics theory, and you have to see that hydrodynamic electron transport is very rare, and most of the methods that we look on are rather gas-like, okay, and have no hydrodynamic part of it. Luckily, I met these three guys. Some of them you probably know. This, and on the top is Karl Landsteiner, then Adolfo Gruschin and Tobias Meng, and they had a solution for this kind of problem, and a very different approach. So starting from the action and the comparison from thermal gradients and gravity, they could actually show by extensive calculations, I will not go through details now, but just show the results, that for a Y semi-metal in the few Landau level regime, right, the thermoelectric conductance, so the current that the diffusive electrical current in response to a temperature gradient has some notion of the gravitational anomaly. This is this part here. This is the magnetic field to the square here, right, in parallel magnetic fields. And here you can see this is the prefactor of the gravitational anomaly. And the nice thing is here is that if a gravitational anomaly exists, right, then in these methods, this part here would be non-zero. This is the essential was the essential link to our experiment, right? So if you would repeat the same experiment as for the chiral anomaly and exchange the electric field by a temperature gradient, then only if Ag, so this prefactor here, exists in reality, then you should see a similar behavior in longitudinal magnetic field. A square root dependence actually in the few Landau level regime, and in the quantum limit where only one Landau level is occupied, this GT, so the thermoelectric conductance, should go to zero. So in our picture, it works like this. It's still the same argument. So if you would heat a metal on one side, right, then you would get an electron flow because hot electrons diffuse through the metal from the hot to the cold side. However, in Y semimetals, this diffusion is heavily suppressed. Okay, and again, because of the conservation of the chiral symmetry in the system. Right? It's the same argument with left and right movers as we had before. But now Carl and Adolfo and Tobias predicted, now if you apply a magnetic field in parallel to your temperature gradient, then the chiral symmetry is broken and current flow should be allowed. And we did this experiment. This is a numeric calculation, how the curves should look like. And here in the low field limit down here, you should get a term that is proportional to the chiral anomaly prefactor, the gravitational anomaly prefactor, and the B square. Okay, so this is the experimental signatures, and it should, of course, occur at the same time as the chiral anomaly if you exchange this temperature gradient by an electric field. So we did this experiment. It's really in the same mindset as before. And this is again here our niobium phosphide Y semimetal. And now on this side here, this is a 4-point thermometer. This is a 4-point thermometer. This is an electrically insulated but thermally connected wire. So we push a high electric current through it. This is a heater basically. Then a temperature gradient builds up along this wire. We can measure the current flow that is the diffusion current that is generated by this temperature gradient through the niobium phosphide, and measure its magnetic field dependence. And we did this experiment, and if we apply now a magnetic field perpendicular to the temperature gradient, current flow is heavily suppressed in these materials, right, as you can see here. However, if we then rotate it again, the magnetic field in parallel to the temperature gradient, then suddenly we observe a strong enhancement of the electrical current. And the shape of this thermoelectric conductance is consistent with an effective axial gravitational anomaly occurring in the system. Exactly. Now the question is, of course, okay, now in this thermoelectric response, it's actually easier to measure experimentally, right? But one would like to ask, is there actually a chance to measure the actual gravitational anomaly alone? Because if you go back to this description, here you always measure a mixture of the chiral anomaly and the actual gravitational anomaly. And And to do this, and the answer actually from Carl's calculation is yes, you should be able to probe the gravitational anomaly prefactor by its own in thermal transport experiments. So what you do then is you heat, basically. So you heat and you apply a temperature gradient, and you measure the heat current that flows here through your system. And this should be heavily suppressed, again, due to chiral symmetry and considerations, if you do not apply a magnetic field. But now if you apply a magnetic field, you should see a heat current to emerge. And these are very primary experiments because they are heavily complicated. For this, we didn't use niobium phosphide because it's hard to handle, but we used a so-called Dirac material that is called zirconium pentatelluride. It doesn't matter, but what it is in detail, it's a metal, but it's a metal with massive Dirac fermions. as quasi-particles. There are no other pocket around. It's one single type of massive Dirac fermions. And then we measured the thermal conductivity of these metals. You can see here a little bit the setup. In the middle here, there is this zirconium pentatelluride wire, and these are thermometers and all kind of stuff to cross-check. And what you can see here is if a measurement when your magnetic field is perpendicular to the temperature gradient that is applied along the zirconium pentatelluride wire, and you can see that the thermal conductance is actually suppressed. However, as soon as you turn your magnetic field into the direction of the temperature gradient, you can see that we see that the thermal conductivity is actually enhanced, so heat flow is enhanced, and this is so consistent with the prediction of the gravitational anomaly. The data here is very preliminary. We have new and very nice data. I wasn't able to prepare them for a talk until now, but we have reproduced this now and have a nice temperature dependent and so on and so forth. So these effective, so it seems that the axial gravitational anomaly is actually observable without the Kerr anomaly in such condensed matter systems. Okay, so far so good. I have plenty of questions regarding this part, which I will phrase in the end for a little discussion. But before I get there, I'd like to just glimpse another thing that we're doing, because we're dealing here with gravity, and that is playing with the crystal symmetry of these crystals that we have. And this is motivated by a very inspiring paper by Wolovic, where it says, okay, if you have such Dirac and Weyl materials, and you, for example, and you strain them, so you basically pull on them or push them together, then you can actually change the effective metric in these systems. And the goal would be, of course, to create a black hole in the end, right, where you basically tilt the cones also. And the proposal here is that you do this by inhomogeneous strain in such a material, right? And we are not so far, but what we have started on now is we take our Weyl semimetals now and just pull on one side. Yeah? And what you have then is that you break the crystal symmetry, and what is funny is then that you basically create, by this pulling, you create basically relativistic fermions with different metric at the same time in your material. We're not sure if this is good for anything now, but it's just an observation that we made. So these are the experiments. This is an unstrained sample, and what you see here, this peak is basically the peak of one of this. And so what we measure here is Shubnikov-de-Haas frequency. Yeah, this is just a measure of the size of the Fermi surface. And now in the unstrained case, we have basically, so only Fermi surfaces of one size. That's what this is telling you. And however, when we applied strain, this is again to niobium phosphide, then what you can see is that this peak here splits very nicely, and we get suddenly two kind of Fermi surfaces in our material with different metric, right? So they have different Fermi velocities, effective velocity of light, and so on and so forth. And this can be very nicely tuned. We're not sure whether it's useful yet, but of course, we will also try to twist things and bend things and do this inhomogeneously. Okay, very good.
Can I ask a question?
Yeah.
When you pull on this, does it create an asymmetry of the Fermi surface?
Yes, exactly.
So can you say more about the sample that you're using, how you are pulling this and to what extent?
It's niobium phosphide. It's again niobium phosphide. And you have a fourfold symmetry in the beginning, and then you break basically one of them and you get a twofold symmetry. That's all.
Okay.
Right? From a condensed matter perspective, it's not so spectacular, but that you can really see and control this is in a wire material was quite nice for us, right? So this is the first step. Exactly. Okay. But same, actually, we did also now strain experiments on, for example, on zirconium pentatelluride. And there you can, because it's a very soft material, you can see very strong changes in the band structure, and you can play with the effect, with the masses of the fermions and with all certain kind of stuff. It's very funny.
Is it affecting spin orbit coupling as well?
Excuse me?
is it affecting spin-orbit coupling as well?
Yeah, it's also affecting spin-orbit coupling. So. Exactly. Okay, but as a reminder before I ask my questions, well, it's maybe a philosophical question, but I thought it's a nice way here to do a nice setup to discuss this. So why high energy physics and real gravity related things, maybe writing real horses, we also always have to keep in mind that we write these quasi horses. And a few related questions to this that I'd like to ask to you guys and to the audience is there actually more to the temperature gravity correspondence than it's a mathematical trick, right? If you read old Tolman papers, it seems it's a real thing, right? So that you basically metric and temperature gradients are strongly related, but in our experiments, I mean, is this how far is it going, right? How far can you draw this comparison and so on? This is something that I would be really interesting to explore and to think about in the future. Then can we observe the gravitational anomaly in true thermal transport? This we have shown that we believe it is the case, right? But we have to it's not so clear. We have to do a few more experiments to settle this. One question that we still have is how does rest mass affect the quantum anomalies also in material systems? Because I mean, as you know, in high energy physics, these quantum anomalies like the Chi anomaly, they exist, but you never have particles. So there are no elementary fermions that have no rest mass, right? And still these are affected by quantum anomalies. Then exactly. So one of the things that needs to be done for sure in the future from the experimental side is that one shows that these anomalies really emerge together with Landau levels, and how is this affected? This has not been shown yet. It's right. This really needs to be settled. And how does it look? How do all these predictions look like if you have really a set of a few Landau level regime and so on and so forth? Right, so it probably needs extensive numerical calculations. Yeah, and then something that plopped up always in this discussion is whether there is a unified description of the temperature gravity correspondence that includes Lattinger, Kalansteiner's picture, Subir Sachdev's picture, Michael Stone work on this, and so on and so forth. And Tolman, of course, to have is there a unified way of viewing this, right? And it seems not so clear, actually, to me at least. Yes, and then this relates directly to the core question: why is it possible actually to measure an anomaly an anomaly coefficient that is obviously tied to curved spacetime in a flat spacetime environment? Obviously, in our lab, we don't have curved spacetime, right? How can a thermal transport experiment in flat spacetime? I mean, how does it know about this anomaly, right? Exactly, and of course, a very general question to you is: are there any more experiments that you would like to see that we can do with our limited setting that we have here? Okay, many thanks.
Thank you very much, Johannes. There's already a question by Evelina posted in the chat, or at least there was the remark question.
Yes. Mm-hmm. So can I ask the following question? I don't know what the real how do you do, but I wanted to ask the question to the talk if I could. Is this okay?
Sure.
Okay, so the question is, so you showed for the zirconium tellurium 5, you show dependence of the magnetic, actually thermal conductance as a function of the magnetic field in plane and out of plane.
Yeah.
But they do not look for small magnetic fields so different, and I'm not sure what kind of functional dependence is actually predicted, what kind of functional dependence I should expect in different magnetic fields.
Yeah, so okay, very good. So there are two things that need to be considered here. So first of all, zirconium pentatelluride has an extremely anisotropic Fermi surface, right? So,
Yes.
and it's kind of a factor of 1 to 10. So to compare these field scales, right, you would have to rescale the field scale of the red curve to make it 10 times smaller, actually. Okay?
I see.
So this is one point, but that's not also the answer. So and we have now so this was a magnet. This was a magnet that is not very stable at small fields, because it can actually, we have data up to 30 Tesla, right? And we have remeasured this low field region and with less noise, and you can actually see a very nice dependence on the magnetic field. And with nice, I mean that you can really see, you can really distinguish between decreasing and increasing thermal conductivity, even in low fields, in the basically limit of infinite amount of Landau levels contributing to thermal transport.
And for the magnetic field parallel to gradient of temperature, should I believe these oscillations, or are they just an error?
Yeah, you should. You should. These are Landau levels, basically.
Okay, so this is really related to the Landau levels. Yeah. Makes sense. Okay, I see. So this is really the peaks, more or less, in density of states corresponding to Landau levels.
Exactly. And why I didn't show this here, but why we chose a 30 Tesla magnet is that you can actually, in this parallel field configuration, can reach the lowest Landau level in these materials.
I see.
And then you have the full range of physics, right? Infinite Landau levels, a few where you see these oscillations, and then the zeroth Landau level.
Thank you.
Thank you. Okay, we have a couple of more questions. First, Silke, please go ahead. Then Maria.
Hello. Thank you for your interesting talk. I have a question related to your comments about having, or the possibility of setting up two different metrics, effective metrics. And my first question is this really a bimetric system, or is it a Finslerian geometry, which is a metric with 4 indices? I'm asking this because if you take a Bose-Einstein condensate with 2 species, you couple them with Raman transitions, like say rubidium 87, 2 different hyperfine states. You can set up similar situation, but you have to do some fine tuning so that you don't get, in all generality, sort of a Finslerian geometry. If you fine tune it, you can have a bimetric system. If this is not familiar to you, another way to look at it, if you change one metric, is the other one unaffected or not? Can you change the right side without at all affecting the left side of your diagrams? So just schematically, are they linked? If they're linked, I don't think it's a bimetric system really.
In shorts on zeroth order, you can change them individually, because you break the crystal symmetry only in one axis. However, you will always have finite scattering, right, between the cones, and I don't know what that is doing to it actually. But it's a fair and very good question. I need to think about this, because I'm actually not familiar with this coupled metrics. But maybe I don't know if I can pull colleagues into this topic, but maybe Roni Roni knows more about this, or Adolfo. Seems not the case here. No, at the moment. That's okay. So I have to think.
I'm not very familiar with this either, but it sounds interesting. Yeah, I haven't thought about the metric with more than 2 components.
Yeah, it's more mathematically that people consider. It's called Finslerian geometries. I could post a link for.
Yeah, maybe you can also post your question in Johannes's channel in the Slack, because then maybe Adolfo and Roni can think about it in the meantime.
Yeah, that would be good. Thanks.
Thank you.
Thank you. Maria, please go ahead.
Okay, so Johannes, thank you for a very nice talk. I would like also to ask about this zirconium pentatelluride, because you try to isolate the gravitational contribution from the pure chiral contribution. But if I understand correctly, when you put a magnetic field, this Dirac semimetal split into a Weyl semimetal. So the cones will split by this chiral separation effect, no? So in fact, in a magnetic field, you will always have a contribution from the standard chiral anomaly, no?
So zirconium pentatelluride. So we picked zirconium pentatelluride because this transition to a Weyl semimetal is actually at very, very high fields. So I think in this direction, in the longitudinal direction, somewhere at 60 Tesla or so. So we can really we know that that we have really a Dirac semimetal. But even there, I mean, the heat is transported by electrons, right? Always. So I mean, the chiral anomaly is probably always there, right? It depends a bit how you measure, actually. It depends how you measure. No, actually not. If you apply a temperature gradient to our system, then heat and electrical charge is transported by the electron system, by the Dirac or Weyl fermions. Now it's a question what you probe, right? So if you and I think you're absolutely right in pointing this out, because the correct way of saying this, are we actually able to probe the gravitational part of the holes of the anomaly that appear in the system individually? I think that's actually the right. That's actually the question that we posed here, because of course in parallel to the heat that we you could also measure the charge of the electrons, and you would see the chiral contribution. That's actually absolutely correct. In our systems, they always appear on the same time. We have a project now where we look into spin systems that don't carry charge in spin ladders, where we search for the pure gravitational anomaly in thermal transport, if you want, so in non-charged particles. And in this system, it would appear probably, we don't know yet, right? Without the chiral anomaly. But that has to be seen. But the question is absolutely valid.
Thank you. And if I can make a little comment about the previous question, I don't think that this is a matter of a biometric thing. I think it's a matter of just having a metric that depends on space. So it's just having a G mu nu depending on X. So I don't think that this biometric thing plays any role. Okay. So straining is simply, first you just see different permeability velocities, which is remotely related to metrics, right? But these biometric are in a completely different context, I think. Okay, just this comment.
Okay, thanks, Maria. Next up is Alexander.
Yeah, hi, Johannes. I have another metric question, quite naive. I understand you want to move towards something like a synthetic event horizon by kind of tilting your cones. Now, I'm always confused about these event horizons, but I understand they're actually kind of a coordinate singularity, in the sense that an infalling observer, I mean, wouldn't notice anything when crossing the horizon. It's just from our vantage point, where we're looking at it, that we seemingly see this kind of singularity relating space and time. Now, I was wondering if you have thought about it. I mean, in your system, do we actually get the real thing, or do we, in quotes, get just tilted Dirac cone? And I'm not sure what I'm talking about. I just would like to understand your perspective.
It's actually it's an extremely good question. And I don't know. Mm-hmm. To be honest, I don't know.
Okay. No.
You're right. You're right. So yeah, okay. So is it, to rephrase? So you think that if one would build such a system, right? That from the observers, from our side, you would see an effective horizon which the particles would not even feel, right? This is in their
right. A particle or an infalling observer crossing the horizon wouldn't notice the thing.
It's a very good question, actually. I don't know. It's good to, okay. I really don't know. Interesting.
Okay. Yeah. Thanks.
Thank you, René.
Yeah, thanks for the nice talk, Johannes. So maybe before I pose my question, can I make a comment on what Alexander was just asked? So in all these analog gravity horizons, no matter whether you have this in Bose-Einstein condensates or real fluid flows or in this situation, yeah, what's happening is that the quantum field theory that you use to describe your excitations, be it phonons, whatever, on a fixed background metric that has this horizon is not invariant under the coordinate transformation that you would need to make to transit from the observer from the static observer to the infalling observer. This is the real point, and hence the vacuum for the static observer is not the same as the vacuum for the infalling observer, which means that and they have a non-zero overlap, and this is where this Hawking radiation spectrum comes from. So from that point of view, whenever you have some effective excitations that live on this metric, and you describe them by quantum physics, then you will find this Hawking radiation, okay? So, and I think this is also going to happen if you tilt the Weyl cone, because it's basically the same fact about the equation that you're trying to quantize. Yeah, yeah. So that's what I wanted to say, okay? And now my question. So thanks for the really nice talk, Johannes. So you were showing this stress and strain experiment where you could tilt the Weyl cones. Can you do this in AC, and at which frequency can you maximally do the stressing and straining?
In principle, we can do AC. These are piezoelectric. This is a piezoelectric setup. So in principle, we can do AC, and then you are basically limited by the time constant of your setup. And what we can drive at the moment, I think, is something like up to a megahertz, so not very high.
Okay, thanks. Yeah.
Okay, thank you. Maybe before we go on to the next talk, one final question. Maybe perhaps, Johannes, you can post your questions to us again if you want to make use of the audience. You can also, I encourage you to post your slides in the Slack channel, of course, perhaps these questions separately even, so people can respond to them. So is there perhaps a final question for Johannes?
Maybe I can, but then I would like to have, I want to insist on one answer of you guys. And this is there more to this temperature gravity correspondence than a mathematical trick? This is something I would really like to know, because we had heavy discussions. So for example, I give you an example, right? We had the discussion in my group doing all of these experiments, and suddenly one postdoc said, and this was very confusing to another PhD student, that he said, yeah, it's just a trick, guys. So it's just a trick. And but is it, I mean, the question is then, is it really, can a particle that experience a temperature gradient really distinguish between whether it's a gravity, if it experiences gravity or a temperature gradient? Obviously, we do not create black holes that basically pull by just heating something in our experiments, and a fire or something like this doesn't attract masses, right? In some sense. I
think there are two answers, but hopefully for you. So I think Maria was just first, and then René. So maybe we can keep it somewhat brief.
Okay.
It feels that this could potentially lead to a discussion which could take very long, and I don't want to. I want the next speaker to have as much time as you had. But please, Maria.
Yeah, very fast. What else is in physics than tricks, mathematical tricks? I think these philosophical questions are out of the question. So same equations, same solutions. Everything is tricks. You should not ask about the essence of temperature or gravity. So if it works, it's okay. That's my answer.
And maybe René wants to quickly reflect on this.
Yeah. Okay. So let me try to add something. In fact, I do not think this is a trick, but I can only give you a theoretical answer, of course. Yeah. So in fact, so people have tried to go beyond what Maria was just alluding to, namely that we are using a lot of stuff in physics to calculate things, in particular in quantum field theory, that are mathematically not completely well understood, like the path integral. And people have tried to do this for a long time to put everything on a more firm footing, in particular mathematicians. And this goes under the name of algebraic quantum field theory. And one of the hard outcomes is that the thermal state in any relativistic quantum field theory is unique in the sense that it is the unique state which has periodicity along imaginary time, and this is where your metric formulation comes in.
Okay.
You can generate the unique thermal state by putting it on a metric, on a Euclidean metric with periodically identified time circle, which we are always doing. So this is a hard result in algebraic quantum field theory. And now you can also, okay, if I now start varying the circumference of this time cycle slowly along my manifolds, I have some small gradient of temperature, then I think this holds basically point by point. So this,
okay.
So this would be my theorist's answer to this. I mean, yeah.
Many thanks.
Okay, thank you. So I spotted some slight disagreement between Maria and René. So I strongly encourage you to fight it out on the Slack channel, just for the sake of having a nice discussion. So thanks again, and then everybody can join and hopefully disagree politely. So thanks again, Johannes, for your nice talk, and please post your questions at least on the Slack channel. Thanks.